Section 8.5 is simple harmonic and damp motion. Simple harmonic motion is anything that travels in a wave. So light waves, radio waves, sound waves, actual water waves, a tuning fork, a pendulum, or a bob on a weight on a spring. So what simple harmonic motion is it assumes nothing's affecting it and it's traveling back and forth in the same motion. So if we look at this diagram here, B would be its equilibrium point. So if it was just hanging down, if a weight was just hanging down on a spring but not stretched at all, C would be its lowest point if you stretched it down, and A would be how much it bounces back up. So it's just going to continue to go back and forth into these three same positions, and its distance over time will be modeled by this sinusoidal graph. It assumes that nothing is affecting it, so no friction, no air resistance, anything like that. As you can see in that picture, the motion of simple harmonic motion looks like a sine or a cosine graph. So that's what we use to represent simple harmonic motion. Amplitude is the same thing that we talked about back in chapter 5 when we were first talking about the graphs of sine and cosine. We have the period, the same thing again. Sine and cosine has a normal period of 2 pi, so we divide that by omega. This new thing we're going to talk about is frequency. So period is how much time passes per cycle versus frequency is the reciprocal of that. It's how many cycles pass in a certain amount of time. So it's 1 over the period or omega divided by 2 pi. For units, period is in time, normally seconds, it could be hours, minutes, days, whatever, some type of time unit. So that would mean that the frequency would be 1 over time or 1 over seconds. 1 over seconds we call hertz. So we represent it with a capital H and a lowercase z, but that is the unit hertz. So whenever you answer a frequency problem, your unit should be in hertz. So the equations for objects traveling in simple harmonic motion are either d of t is equal to a cosine omega t or d of t is equal to a sine omega t. The way you can tell the difference is by what's happening in the situation. So if you remember your sine graphs, they start at the equilibrium point, and a positive sine graph travels up, back through the equilibrium point, down and back up, versus a negative sine graph starts at the equilibrium point, heads down before turning and coming back up. So any function or any situation where the object is starting at its equilibrium point is going to be a sine graph. If it's starting heading up, it would be a positive sign. If it's starting at equilibrium heading down, then it's a negative sine graph. Versus if a function starts displaced, cosine starts away from the equilibrium point. It starts at either the top of its period or the bottom of its displacement. So a cosine graph would be if something starts displaced. So for instance, a bob has been pulled down and then released. If it starts at the top of its travels, then it would be a positive cosine graph. If it starts at the bottom, so for instance the bob pulled down and released, that would be a negative cosine graph because we need it to be reflected across the x-axis. So here's an example. I would pause the video and read this word problem. So you have an object attached to a spring. It's pulled down to start with and then released. And we have some certain information here. So it's pulled down a distance of 5. So that would be your amplitude. Its max displacement is 5 centimeters. It then tells you that the time for one oscillation, so that would be your period, is equal to 2 seconds. And we want to write an equation that relates this situation in simple harmonic motion. So go ahead and pause the video and try and write an equation using sine or cosine that represents this situation. So I know I'm going to either start with a cosine omega t or a sine omega t because those are the equations for simple harmonic motion. I chose cosine because it says that it's pulled down and then released, which means it starts displaced, and a cosine graph starts away from the equilibrium point. I chose a negative out in front because it's pulled down. Normally cosine starts at the top. To make it start at the bottom, we need to reflect it across the x-axis, so we need this negative out in front. And then we're just going to fill in everything that we know. We know the amplitude is 5 because we're told that its maximum displacement is 5. Omega is pi because the period is 2, which is equal to 2 pi divided by omega. Cross multiply and you get omega to be pi. So the equation that represents this scenario in simple harmonic motion is d of t is equal to -5 cosine pi t. So now we kind of have the opposite. We're given the equation for something in simple harmonic motion. D of t is equal to -3 sine of 1/2 t. We know that displacement is in meters and that time is in seconds. And we have some questions that we want to answer. So first thing we want to know to actually describe the motion of the object. So first off, it's simple harmonic motion. We know this because of the equation. But then I want you to describe, is it starting up? Is it starting down? Is it starting at its equilibrium point but heading up or heading down? So you can get all that information out of the equation. And then maximum displacement, the time required for one oscillation, which this is asking for the period. And then our new vocab word, frequency. So go ahead and pause the video and answer these questions. So if we look at the equation, we know it's a sine equation, which means it starts at the equilibrium point because sine starts at 0, 0. So we know it starts at the equilibrium because it's sine, and we know it's heading down because of the negative. That's going to reflect sine across the x-axis and make it go down first instead of going up first. Maximum displacement, that's just your amplitude, the absolute value of it because it's a distance, so 3 meters. Time required for one oscillation, that's asking for the period. So period is 2 pi divided by omega, where omega is 1/2. So one oscillation, one down, up, and back down is going to take 4 pi seconds. And then the frequency is the reciprocal of the period, so 1 divided by 4 pi hertz. So obviously the only time simple harmonic motion happens is if you're in a vacuum. Everything in the real world is affected by some kind of resistive forces. So that's damp motion. Damp motion takes into account these resistive forces like friction and air resistance. So go ahead and pause the video and write down the equation for damp motion. So A is the same A as the simple harmonic motion. It's the initial displacement, so how far the bob is pulled down. B is the damping factor, so that's a value that they're going to give you. They'll say, you know, your damping factor is 0.7 or something like that. M is the mass of the object, and then same thing over here. Omega is the same omega we've talked about. B is the damping factor, M is the mass. Just make sure this negative B over T, BT over 2M is in the exponent of E, and E is our universal constant E, 2.7. So here's a problem with damp motion. It gives us a bunch of information and it wants us to find the equation that represents the displacement of the object after t seconds. So let's go through and find some information. So the first thing it tells us is that the mass is 25 grams. So mass is represented by M. It tells us that we have a damping factor of 0.7 grams per second. So damping factor was B. So 0.7 grams per second. It tells us the first oscillation takes 5 seconds. So that's our period. That's how we're going to find omega. So t is equal to 5 seconds. So go ahead and pause the video, take all this information, and write an equation that represents this situation. So it also tells us that it's been pulled down a distance of 10 centimeters. So we know A is going to be negative 10 centimeters. So then I just fill in everything that I know. This is the equation from the previous slide. So A is negative 10 because it's been pulled down, so that makes it negative. B is 0.7, M is 25, omega is 2 pi over 5 because the period was 5, which is equal to 2 pi over omega, cross multiply. And then again, B is 0.7 and M is 5. So you can multiply things out if you want to. 2 times 25 is 50. 2 pi over 5 squared, if you wanted to, would be 4 pi squared over 25. 0.7 squared would be 0.49, and 4 times 25 squared would be 2,500. Or you can just leave it in this form if you'd like. Either way works. So again, simple harmonic motion, A sine omega t or A cosine omega t is any kind of wave motion that has no resistive forces. And then damp motion is anything that has that same motion, but in the real world has friction, air resistance, spring constants, that kind of stuff.